Why can't you define these simple words? On the surface, it feels almost insulting to ask. You've used words like the, thing, or good since you've known to speak, so surely you must know exactly what they mean. But try it now. Give a clean, precise definition, not an example, not a synonym, an actual definition. Suddenly, the mind hesitates. You can summon endless uses of the word, but pinning it down with the sharp edge of language feels like grasping smoke. That pause isn't a sign of ignorance. It's a window into how meaning actually works in the human brain. Language isn't stored inside us as a tidy dictionary. It lives as a network. Think of good. Your brain doesn't file it away in a folder labeled positive moral value. Instead, it stores a web of overlapping associations. The word connects to feelings of approval, childhood lessons, the smile of someone you admire, the relief of solving a problem, the taste of a satisfying meal. No single definition unites them all, yet together they form a fluid sense of the meaning. Modern AI models trained on nothing but raw text stumble into the exact same solution. They don't build definitions either. They place words into geometric spaces where closeness encodes similarity. Meaning emerges from patterns of relation, not isolated boundaries. This reshapes what it even means to know a word. Psychologists began uncovering this decades ago through something called prototype theory. Ask someone to name a bird, and they'll say a robin or a sparrow long before they think of a penguin. All are birds, but some sit closer to the center of the category than others. It's not that the concept is broken, it's that the categories themselves are built on gradients, with bright cores and fuzzy edges. The same is true for game, art, or friend. Everyone knows them, yet no single feature unifies every case. Definitions crack under the weight of their own rigidity. Neuroscience reinforces this picture at the biological level. Brain scans show that when we think of words, activation ripples across the cortex. Visual regions light up for imagery, motor regions for actions, emotional centers for feelings. Then, hub areas integrate them into a cohesive sense of meaning. Researchers have even mapped vast semantic landscapes across the brain. Related ideas cluster together, but bleed into one another without sharp lines. Meaning is literally painted across space in gradients of activity. AI models echo this architecture almost uncannily. Systems like Word2Vec, or GPT, arrange words in high-dimensional maps. Cat lands near dog, kitten and pet. Chair drifts to another neighborhood entirely. The geometry itself encodes meaning. And here's the remarkable part. These machine-learned maps can actually predict patterns of human brain activity when we think about words. Without being told how language works, the algorithms stumble onto the same relational structure that evolution carved into us. The implications of this are enormous. For AI, it shows that understanding doesn't emerge from definitions, but from immersion in patterns. A machine trained on billions of words never needs an explicit definition of love or truth. It learns them by mapping their countless uses and letting meaning emerge from the position in the web. This is why AI can write, translate, or even generate poetry. It doesn't know the dictionary entry for good, but it knows the shape of good in the network of language. That shape turns out to be all that is needed to mimic understanding. For humans, this sheds light on why communication works as well as it does. You and I don't need identical definitions in our heads. We only need overlapping maps, and those maps are consistently updated as we live, read, and interact. Two people can never perfectly agree on what freedom means, yet both can use the word fluently because the shared regions of their conceptual network align enough for meaning to pass between them. Misunderstandings, debates, even political conflicts often trace back to where those maps diverge. Understanding this doesn't just explain confusion, it offers a strategy for resolving it. If you want to bridge disagreement, the solution isn't to argue over dictionary entries, it's to explore the neighbors of meaning that people are actually drawing from. In AI research, this principle has already opened new doors. Models that use relational maps of meaning can generalize better than those that rely on fixed definitions or rigid rules. When an AI knows that doctor is close to nurse, hospital, and medicine, it can infer connections it was never explicitly taught. Humans do the same thing when we guess the meaning of a new word from context. This ability to interpolate within the web of meaning is what allows both humans and machines to adapt. It's not just about knowing words, it's about navigating the geometry of concepts. Even in neuroscience, this understanding is beginning to transform how we think about thought itself. If meaning is distributed across regions, then disorders of language and memory aren't simply about losing definitions, they're about distortions in that relational map. Alzheimer's, for example, often erodes categories at the edges before the center. Patients may know what a bird is, but struggle to identify a penguin as one. This is prototype theory playing out in pathology. By studying these gradients, researchers are finding new ways to trace how cognition unravels and how it might be supported. It also reframes what it means to teach or to learn. If knowledge is a web rather than a list, then true understanding requires weaving connections, not memorizing definitions. This is why students often know a word in one context but fail to transfer it to another. The connections haven't yet spread across enough of the network. Education, then, becomes less about reciting crisp answers and more about cultivating rich neighborhoods of meaning that can generalize across situations. The lesson extends far beyond language. The same relational structure underpins how we grasp morality, identity, and even reality itself. Words like good or true or real resist definition not because they're meaningless, but because they point to vast networks of overlapping concepts. Each person builds their own map, shaped by culture, experience, and perspective. That flexibility isn't a flaw. It's the very thing that lets language, thought, and society remain adaptable in a world that's always shifting. And this brings us back to the simple words that started it all. Function words like the shape the skeleton of language without ever pointing to an object. Verbs like run scatter into dozens of uses, each perfectly clear in context but impossible to condense into a line. Abstract ideas like love or freedom spread endlessly through different neighborhoods of thought. They all escape definition because definition is too rigid a tool for how meaning actually works. The very words that seem simplest often reveal the deepest truth about cognition. Our minds don't work in binaries and fixed definitions. They work in overlapping gradients. They work in relational geometry. They work in webs too intricate to capture with a sentence. And that flexibility is not a weakness. It's what allows us to improve, to adapt, to understand one another without ever carrying the exact same dictionary in our heads. So, the next time you stumble trying to define a word you use every day, don't see it as a failure. See it as a reminder. Language is not a set of cages. It's a living network. And the words that resist being pinned down are the ones that show us most clearly how that network works. They reveal not just why definitions fail, but why thought itself succeeds.